Hey there, my name's Mike, and welcome to my channel. This is a book about differential equations, and if you're going to teach yourself differential equations, get this book. This is Fundamentals of Differential Equations, and it's written by Arkant Nagel and Edward B. Saff. It comes from us from the University of South Florida. This is the third edition, and it was published in 1993. Might I add, this book is so 90s. It's actually kind of hilarious. One of the things they mention in this book for features for the student are digital graphics, and then you look at the digital graphics that they have, and it's like a couple cool curves that have been plotted, and at one point, for one moment, they do show a sphere in 3D. So very 90s, very fun. But this book will teach you differential equations, and it's a really useful field to know, and this book will tell you that. So the book starts off giving you a solid background, and there's all sorts of really cool ways that differential equations are used in a science type field. So in engineering, you have things like heat transfer, Newton's law of cooling, and then on physics background, you have things like oscillatory motion, which is kind of the foundational stuff you need to know to understand really high-level concepts like quantum mechanics, harmonic motion. It all comes from a differential equation that we're able to solve. So bringing you a little closer here, if you want to teach yourself differential equations, one, get this book. It's about 40 or 50 bucks on Amazon, well worth the money, but let's go over the stuff that this book teaches you. So first, it'll tell you what a differential equation is, and the really short SparkNotes version of this that I'll give you, and I do recommend you pick up this book, but if you're familiar with calculus, and please don't attempt to learn this stuff without calculus, you do need to know how to differentiate and integrate functions beforehand, but if you want to learn about differential equations, basically the idea is that you have a function y of x, and they put an x value and it spits out a y value. Then we know that if we want to find the slope at any given point, then that is the derivative dy by dx, right? Right there, that slope is a derivative. So what if I don't know why, but for some reason or some other, usually this happens when we do data science, we know how the function changes, and we have a dedicated function that describes this. So maybe it's like some function of x and y. Maybe it's something like x squared plus xy. We know how it changes, and at any given point, I can tell you what the slope is, but I can't tell you what the function is. The goal of differential equations is to use certain techniques to work backwards to figure out what the function y of x is, given we have its differential form, which is dy by dx, or sometimes the second or third or fourth order differential equation. But we don't know why. We just know dy or d squared y. And so all these things are very important, and this book will teach it to you. It starts with an introduction to it. You learn something about something called direction fields, which are really beautiful pieces of mathematics. I like to think of them as the gears that make equations work under the scene of things. So if I graph y equals x squared, the direction field is kind of a way of imprinting the ghost of that function without seeing it. I don't have time to explain it super in depth, but I can show you what they look like, and they're really pretty. Once you gain your bearings a little bit and understand what direction fields are, the idea of differential equations, and this whole stuff right here probably take you about 3 or 4 days to get under your belt, then you get into the meat and potatoes, understanding first order differential equations. This stuff is probably 50 to 60% of all the differential equations you'll have to deal with in physics and engineering. A lot of things can be represented as a first order differential equation. You don't have to know what that means right now, but the book will, of course, teach it to you. And you're introduced with a really cool problem. You talk about the motion of a falling body. And one thing that's really nice is if you are following this channel's Foundations Physics series, where we teach ourselves physics from start to finish, then you might actually be familiar with this, because this is how we introduce Newton's laws of motion. This is the second law, force equals mass times acceleration. And this book explains how that's actually a differential equation, or at least one way to write it as such. Then we talk about, once we've introduced the topic, we talk about ways to solve differential equations. Like I said, sometimes these are really, really ugly functions, and so we need to use really special techniques to solve them. Separable equations, exact equations. These are all types of differential equations, and the book will teach you how to take something like this, m dx, that's where m is a function, plus n dy, and turn it into something like this. We take these like half differentials of a function and turn it into a function of x and y, and we do some really cool integration to get there. And the book walks you through the proofs, it walks you through the example problems, and then finally it lets you do some on your own. So it's a very thorough example. If you're teaching yourself differential equations from start to finish on your own, then you want to learn all of this right here. And the good news is the book is really good about explaining this, so this shouldn't take you very long. But start with separable equations, do at least 5 or 6 of the example problems. And those example problems look a little bit like this. These are all the exercises from that chapter. And so we have to determine whether the given differential equation is separable. We don't have to solve it. These, we do get to actually solve them. And so we have all these dy by dx, and we get that slope. We have to find a way to find y from that. Once you feel really, really good about that, you can move on to exact equations and linear equations. Understanding this might take you a little bit. Once you do, linear equations will make a lot more sense though, because linear equations are basically a subset of exact equations. Once you see that a function is linear, then you're able to apply the same rules that you learn in exact equations to it. You just have to do a couple things. You have to use something called an integrating factor, and that's all taught about in here. The cool thing about differential equations is if you want to speed run it, and I don't recommend this, but really it comes down to knowing a couple key formulas to use, and they look a little bit like this. So if I have a function, this is a standard form function, then I'm able to write the function of y. So if I have a differential function like this is how we do integrating factors. If I have a differential equation, it looks like this. So y prime, or dy by dx, is equal to some function of x, p of x, times y, and that whole thing is equal to a function of x called q of x. And that means we have variables of x here. Here, we have variables of x multiplied by a single y, and then here we just have like dy by dx. That's it. There's no function going on. Then we can use very, very simple rules to find y using this integrating factor. You can just do this and do it fine, but the cool thing is this book will walk you through the proofs to actually understand what it is that you're doing, which I think is really nice. Finally, you get into substitutions and transformations. This is like 2/3 of the way through a course at the college level of differential equations. And the cool thing is that all of this is just ways to take functions that aren't these and make them into things that you can solve. And so that's basically the last, from page 55 to like through 60, that's what you're doing. This chapter about mathematical models is really, really cool. Honestly, you can probably skip most of this. You should learn about Newtonian mechanics, though, because it's kind of cool. So I recommend you check these out, but skim through them. Don't feel compelled to learn everything. Then you can do linear second-order equations. This part of the book is pretty theory-heavy. There's some matrix algebra that kind of comes into play. Concepts from linear algebra come up again, and it took me a little bit to get past this. So 4.1... 4.2, this idea of a linear differential operator, that took me quite a bit of time to figure out, but you can do it. So take your time with chapter 4, understand what this differential operator is, and then once you get into things like reduction of order, it makes a lot more sense, and you can get into the kind of big meat and potatoes of this. So homogeneous linear equations with constant coefficients, these will come up in a class, as well as superposition and non-homogeneous equations. These will all come up, but at this point, really the key things that you want to understand are homogeneous linear equations with constant coefficients, superposition, auxiliary equations, and then the variation of parameters right here. This will be something that you use a lot if you took a proper course in it. If you have a friend who you've also convinced to do math, because maybe you're both masochists, then you can go here and do some group projects together. These group projects are super cool, but admittedly really kind of mathematically dense. So if you do these, what you might want to do is write all this down in a notebook and then spend a day or two learning how to actually do this stuff, because it is cool to do. But like I said, it's effort intensive. It is worth it though. It's neat. Chapter 5 is exceptionally fun because instead of doing all the stuff you need to solve differential equations, you're still solving them, but now you actually get to learn different ways that it applies to the real world. So damped free vibrations. A lot of this stuff is covered in physics very, very briefly. Damped oscillatory motion. You're given a single equation and they say, there, do it. This time, you actually get to derive that equation and figure out what it is that you're doing. Force vibrations, elementary circuits. Circuit analysis is a big one, and you see this a lot. So it's cool. You can just do the stuff that you're interested in. At this point, once you've finished all of this in Chapter 4, you're mostly able to do most stuff with differential equations. You are 80% of the way there to understanding all of this topic. Finally, the key thing that you should aim to learn if you read this book is this guy right here, the Laplace transform. This is a really cool transformation you can do that allows you to describe a function in terms of a sort of parameter of other stuff. So the Laplace transform is really, really useful, and I recommend that you take a lot of time to learn this. What's really cool is, again, this book explains everything with a really cool introduction. So we get a simple electrical circuit. It looks a little bit like this, and we get to describe Kirchhoff's laws in differential equations. And those look a little bit like this. So we do something called a Laplace transform here, and it's defined right here. And you can see that it's basically this really neat integral that we can do on a function that takes a function of time and produces a function of a parameter s. Again, very useful stuff. You can then play around a little bit further once you've done the Laplace transform. Some of these chapters are marked as challenge chapters here, which is, if you're wondering what that asterisk means, it's usually not something that's taught, but it's really cool to learn. So the Dirac delta function is really, really neat. A little bit beyond the scope of a lot of people's like kind of base knowledge, but if you do learn this, you can brag to someone who might find it interesting. You certainly will, though. And then finally, we get into systems of differential equations and their applications. And the rest of this book is more or less application stuff. Here we have a little bit of matrix methods, which is basically telling you, hey, you did all this stuff before, now we're going to show you how to do it in a way that you can use matrices, which can clean up your work a little bit. It might be confusing at first, and that's what a book like this will do. So if for some reason you really, really like the matrix stuff, you can pick up a book called Differential Equations, A Modern Approach, which is this, but like multiplied by 100, and it's just a ton of matrix math and linear algebra, which is all this. Finally, you get into partial differential equations, and most of quantum mechanics deals with stuff like this. So it's really cool that you can learn this stuff. The Fourier series, heat equation, the wave equation right here. If you want to learn quantum mechanics, this is an excellent point to start. And then you're finally done with differential equations. So this is the book to get if this is something that you're interested in. I recommend it. Like I said, you can find it usually pretty cheap, and it will teach you all the things that you need to know. Maybe at one point we'll even do a video covering some of the topics in this book, because differential equations is really cool. Like I said, it's like the final boss of algebra. So do go ahead and check this book out. If you have any questions, leave them in the comments below. And if you like these sort of book review type content, let me know as well, and I will continue to produce more of them. So thanks for watching, you guys, and I will see you in the next one.